we are looking at 9.2 function characteristics. We are going to talk about the different function families and their differences. We're talking about 3 different function families today. And I think we've seen all 3 of these already. Might have been a minute since we've talked about a couple of them, so we'll go over what all of those mean. The first function family that we're going to talk about is the linear function. Linear function contains the word line. An equation example for linear function is something like y equals 3x minus 4. Something like y equals x minus 2 divided by 7. Those are examples of linear functions. Now, that word line inside of linear tells me that when I draw the graph of a linear function, it should look like a line. It can be a line going upwards, going downwards, horizontal, vertical. As long as it's a straight line, that's an example of a linear function. So the characteristic here, we're going to write straight line. So we are going to be identifying our functions in 3 different ways. One will be looking at equations. One will be looking at graphs. The third way we're going to identify our function is by looking at a table of x and y values. We've done these tables before, but we are going to look at a table that's already filled out for us and then determine what the pattern is. For a linear function, the pattern is going to be repeated, addition, or subtraction. Can I spell that? Subtraction. Of the outputs. Remember, outputs represent the y value. So if I'm looking at a table of values, usually it'll be on the right side of the table, unless your table is horizontal, which we'll see. Any question on linear functions? We remember kind of looking at those way in the beginning of the year? Yes? Maybe? Okay. The next one is called quadratic functions. This is what we spent the last 2 units talking about, was these quadratic functions. So hopefully we're kind of familiar. The first example of an equation, just like we saw way back when, let's do 3x plus 4 or something like that. Those are all of the equations that we talked about last unit, right? Every single one of those is quadratic. We might also see something in this unit that looks more similar to this. In parentheses, x minus 2 squared plus 11. Either one of those is an example of a quadratic function. Does anybody remember what the graph of a quadratic function looks like? What did we call the shape of these graphs we talked about all last unit? James? Parabolas. So a parabola kind of looks like this, right? That's the characteristic we're looking for, is that parabola. Good there? Now again, let's talk about the table patterns. We made our own tables. Way back in the day, we made our own tables for graphing these quadratics. If you didn't know, there is a pattern in those tables. I'm going to write it out for you, and I'm going to wait to explain it until we get to the tables, because it's a little bit of weird things that doesn't make sense until you actually see it. So the table pattern is called second differences in the outputs, which again, remember, outputs represent the y values. And those second differences are the same. If we see that in a table, then we know that's a quadratic. I will explain to you exactly what that means when we get there. For now, just write that down. Any questions on quadratics? the last one, and we got to really rewind to get to this last one because it's been a very long time. But we did talk about these. We graphed these with our tables as well. Are those exponential functions? Maybe this will jog your memory. They look something like this, where I have y equals like 3 times 4 to the x power. Or maybe it had a bunch of fractions in it, and it was like 1/2 times 2 to the x power, or something like that. Oops, not 2. 2 to the x. Okay, that exponential, this first part, x, tells me in those equations, the exponent is an x. Exponential exponent x. Okay, that's how I remember. Again, we did graph these, but I know it's been a minute, so let me refresh your memory on what these look like when we graph them. They end up looking something like this. That's an example of a J shape. They could also go this way. They could be upside down, either one of the ways, but they kind of make these L or J. I'm going to write a J like this. L or J shapes. When we graphed these in our tables, we were able to skip some steps because we were able to find patterns in those tables. The pattern that we used way back when we did this was that there was always going to be repeated multiplication or or division in the outputs. So again, when we did these way back when, we figured out what was the pattern. We were able to go from there and get more points. Now I'm telling you, you're looking for multiplication or division to find exponentials. Any questions on these? Okay, so like I said, we're going to be able to identify these in 3 different ways. The first way we're going to identify them is just by looking at the equation. When we look at the equation, we are going to look at the degree of my equation. Remember what degree is? It's like the highest exponent in that equation. So if I take a look at my linear function examples over here, what degree are these? 1. The highest exponent in all of these is 1. So these are like first degree. What about in my quadratics? What's the highest exponent here? 2. So we call quadratics, those are second degree. Remember from your table of linear, quadratic, cubic, all that good stuff. One that was not in there was exponential. What's the highest exponent in this equation? It's an x. So we call this xth degree. We're just looking for where that is an x. So anytime it's an x, it's exponential. Okay. That's literally all we got to do when we were looking at these equations. So let's take a look at A. And I want you to raise your hands, please. Letter A. What do we think? Linear, quadratic, or exponential? Cody? Perfect. Letter B. Jacob? That one's linear. We have an exponent of 1. Okay. C? Adriana? Exponential. I said raise your hands. I'm on letter D. Cody. Letter E. Jacob. And letter F. Cody. Beautiful. Any questions on that? Flip it over. Again, let's raise our hands. We're going to look at the shapes of these graphs. What is letter A? What shape is that first?
I don't know.
Cody? Yeah, but what shape is that called?
It's a parabola.
It's a parabola, so we call that quadratic. Letter B, what do we call that? Linear, because it is a straight line. And then letter C?
Exponential, because it's an L or J shape.
L or J shape. Perfect. Any questions on those ones? Okay, now we got to lock in. Because now the table ones get a little confusing. When I take a look at the tables, I am always going to take a look at the outputs. So the outputs in a table are either going to be f of x or they're going to be y. So maybe circle those so you can see what we're looking at specifically. If you're the type of person who can look at a table like this and see the pattern super quickly, that's fantastic. I want you to write that pattern down so that you can have some kind of like evidence of work. If you're the kind of person who doesn't recognize patterns that quickly, that's totally fine. Let me tell you how we're going to do these. We are going to first see if there's a pattern of addition or subtraction. I find that that's the easiest pattern to identify. So let's say I look at this, I don't see the pattern right away. I'm going to figure out what is the difference between each one of these steps. So from 2 to negative 6, I'm subtracting 8. From negative 6 to negative 14, I subtract 8. From negative 14 to negative 22, I subtract 8. My first try, or my first attempt at finding this pattern ended up being the correct one. I'm repeating the subtraction of 8. So what do we call that, Cody? Linear. So we are going to say it has repeated subtraction of minus 8. Good? I'm going to take a look at letter B. Again, I don't see any pattern here, so I'm going to go for my first option, which is always to see if I have addition or subtraction. I'm going to start by counting. This is like plus 3 halves, I think. This is plus 3. This is plus 6. Is that a pattern of repeated addition? So I got to try something else. The next thing I'm going to try is multiplication or division. What do we multiply by? Every single step we are multiplying by 2. So there is my pattern. When I'm doing repeated multiplication, what do I call that? Exponential. Okay. Last one. Again, maybe I don't see a pattern. That's okay. I'm going to start with addition and subtraction, and I'm going to figure out, is it a pattern of addition or subtraction? This is plus 3. This is plus 5. This is plus 7. Is that a pattern?
Nope.
No. Do I have a multiplication pattern? Let's back it up. Is there something I can multiply these by to get to the next number? Anybody?
Nope.
I don't see a pattern of multiplication either. So here's my third option. Let me go back to what this is called. Remember I had you write this down? It says second differences in the outputs are the same. Right here, what I have written down, these are our first differences. They are the initial difference between each one of these numbers. So then what do you think the second difference is? It's going to be the difference between these numbers. What's the difference between 3 and 5? Plus 2. What's the difference between 5 and 7? Are those two numbers the same? So these are our second differences. They are the same, so therefore we can call this quadratic. And our reason, second differences are the same. Any questions on that?